AP Chem. This is your day 37, 38. I'm also going to add day 39, which was Friday. So this is going to be worth 3 lessons. It's a long assignment. It's a challenging assignment. So I want you to really study this assignment. You have 3 days to do it. I pushed the due date back to Tuesday. I would like you very much to work on this assignment and be sure you know how to do these problems. Solution stoichiometry is really central to chemistry. And at first it's difficult. It's the most difficult type of stoichiometry, which is why I saved it to last. And it is something you do need to master. Because in a science lab, generally, in a high school science lab or chemistry lab, we're generally working with solutions more than anything else, certainly more than gases. So go ahead, study this, practice it, and get good at it. Okay, so let's go. For this assignment, you really need 2 sheets. Your measures of concentration, which is in the reference sheet section of Canvas, and just a standard periodic table because you're going to need to figure out some molar masses. Okay, so let's go ahead. So it says, what is the molarity of 2.3 moles of potassium hydroxide in 250 milliliters of solution? The original assignment that said water, and I changed it. Okay, it has to be solution. Water will be incorrect, so let's understand why. The definition of molarity is right here. It's moles of solute over liters of solution. So molarity, you can just write it here on your sheet, equals moles of solute over liters of solution. Solution is the solute and the solvent mixed together. The solute here is potassium hydroxide. The solvent is water, H2O. And when you mix the two of them together, you have the solution. So this formula, you have to have solution, not solvent. Water would have just been the solvent. You would not have been able to solve that problem. Okay, so let's go ahead. How do we get this going? So in this case, we're looking for what is the molarity. So whenever you work one of these molarity problems, break molarity immediately. When you see its molarity, or capital M, break it into these component units. So it's moles. Okay, so in this case, it's moles of KOH for liters of the solution, KOH plus H2O. I don't write it like this normally. I'm just doing it to, again, emphasize what solution means. It's the two of them mixed together, everything mixed together. Okay, what are we starting with? Well, you got a couple of numbers here. This is going to be kind of an intermediate number, okay? But what you're going to really start with here is this, is moles of KOH. So you're going to come way over here. You don't know how much space you're going to need, so let's write this way over on the left. All right, and so we see we have 2 parts to the answer, a numerator part and a denominator part. We'll just call it top and bottom. So the top part, moles of KOH, is already set. You don't have to change that at all. But what it is, it's per 250 Okay, so that's the solution. And normally we'll write it just SOLN. All right, so what do you see happens here? Moles KOH, nothing needs to be done on top. On the bottom, you have milliliters of KOH plus H2O solution. You got to get it to liters. So you're going to use this conversion right here to do that. And you got to think about what do you need to cancel out and what do you need to appear where. You need liters to appear on the bottom here. So I'm going to take this conversion and put 1 liter, and that's of solution. And on the top is the 1,000 milliliters, because you need that to cancel out. And again, it's always unit of measure and what the substance is. So milliliters of this, cancels. You have liters of solution down left on the bottom. You already had the moles on the top, so everything is set up to go. And what I would advise you to do is see if you can practice doing a little mental math on this, okay? So if I do mental math, I see that 1,000 divided by 250 is 4. And 4 times 2.3 is going to be 4 times 2 is 8. 4 times 0.3 is 1.2, so that's going to be 9.2. So that's going to be the answer. Why do I say that? As I mentioned in class, that on the multiple choice portion of the test, you're not allowed to use a calculator, and they will give you numeric problems. They won't give you really tricky ones, but they're going to expect you to kind of be able to do some mental math. That's part of what they're testing you on. So as we have time, we'll practice that. But what you can always do on every problem is practice it on your own. When you set up an equation, see how close you can come. Try to do the whole equation in your head and see how close you come to what you get when you do it on the calculator. Okay, let's keep going. How many moles of hydrochloric acid are there in 357 milliliters of 1.7 molar aqueous solution? So aqueous solution means a solution of hydrochloric acid mixed with water. Anytime, by the way, you're dealing with one of these problems and they don't say that the solvent is water, you can assume it's water. Okay, so we're going to go ahead. So it's asking us for moles. And over here, we're going to start with this, 1.7. And it's HCl for chlorine. It's not HCI. It's hydrogen and chlorine, hydrochloric acid. Now on this one, you already have a denominator. So you're not going to put the 357 there. You're going to put 1 liter. Okay? So there's moles per liter. And that's not liter of HCl. It's liter of, you tell me, what's that liter of? Let's get an eraser here. Okay, of solution. This time I'm not going to write out the way I did up here. That was solution also, but I'm just going to write SOLN. Okay, so let's look at what we have. We have moles of HCl on the top. We want to end with moles of HCl on the top. That's good. Here we have nothing on the bottom. You could put a 1 there if you want, but there's nothing there. So we've got to make liters of solution disappear so that there's nothing left on the bottom. Okay, so we have nothing on the bottom. We need to make liters disappear. So we're going to put it up on the top here, and we're going to use the conversion we used before. 1 liter of solution for every 1,000 milliliters of solution. So liters of solution cancels here and here. Again, 1 liter for every 1,000 milliliters is anything. It doesn't matter what you're dealing with, but you need to be sure you're specifying what it is you're canceling. Solution. Now we have 1,000 milliliters down here at the bottom. We don't want that. We want nothing. So how do we cancel out milliliters? Now we go to this number right here. This subject is all about learning how to line up the units. Let the units lead you through the problem. Okay? Alright, so there you got milliliters and it's of solution. So milliliter solution cancels there and there. So the only thing you have left is moles of HCl on the top, and that's all you want left. So you can go ahead and compute the answer. 1.7 times 1 times 357 divided by 1 divided by 1,000. And that will give you 0.606. And 2 significant figures there, so I'm going to call it 0.61. Okay? Again, study these problems. Once you've finished writing it down, go back and look at it. How did that work out again? What were the steps? When did I need each of these numbers to come into the problem to make the problem, to solve the problem? And I promise you with practice, you'll get good at these. Okay, on the next problem, what is the molarity of 5.4 grams of NaCl dissolved in 0.24 liters of... It has to be solution, not water. Because that's the formula for molarity, and this is a molarity problem. If it had been molality, there's a way you could have solved that. We'll get into that later. Okay, but it is molarity. All right, so it says, what is molarity? So you're going to come way down here, and molarity is moles. In this case, the solute is NaCl. And it's dissolved in 0.24 liters of solution. Okay, and what we're starting off with is 5.4 grams. And it's dissolved in 0.24 liters of solution. Okay, and I made an error writing 0.24 here. It should just be liters of solution. Okay, so we need some liters of solution on the bottom. We need moles of NaCl on the top. So liters of solution is good. We've already got liters of solution. We don't need to do anything to the bottom. But we need to get from grams of NaCl to moles of NaCl. That's going to require a molar mass conversion. So we can kind of sneak that down on the side somewhere. So Na is 22.99. Chlorine is 35.45. There's one of each of those, so you add those together, and you get 58.44. So I'll write that down here. Okay, there's the molar mass conversion. So we're going to put one of these on top of the other, or the other way around. You've done this 1,000 times, okay? So which one goes on the top and which one goes on the bottom? So the grams of NaCl cancels out, and we end up with moles of NaCl over there. Well, we need grams of NaCl on the bottom. Grams cancels with grams, and we have moles on the top. We already have liters on the bottom, so now we just have to run those numbers. 5.4 times 1 divided by 0.24 divided by 58.44, and that's going to give us 0.385. Two significant figures here, so 0.39. And you can write a really long equal sign there, okay? Nothing else goes in between those two. All right. Okay, you want to create 500 milliliters of a 1.2 molar NaOH solution. How many grams of NaOH would be required? And this is a typical AP problem that they might ask you. It's something you might be asked to do in actually our class in a lab once we get back there. I'm going to tell you I want you to make 500 milliliters of a 1.2 molar solution of NaOH. So go grab the NaOH, and how many grams are you going to need? Weigh it out and mix it with the 500 milliliters. So this is a practical lab problem. So it's asking how many grams of NaOH. So we're going to come way over here. That's sodium hydroxide. We'll use that frequently in class. It's used in cleaning solutions. If you look at some of the stronger cleaning solutions, it will have that. Okay. All right. So what are we starting with? Well, we're starting with 1.2 molar NaOH. So it's 1.2 moles and that's for every 1 liter of solution. You may wonder, when do you put this one on the bottom here and when do you not? Well, in this case you can't, because you've got molarity and it's already got a numerator and denominator, so you simply can't put it there. But it'll start to become apparent when you do it, when you don't. So what are we looking at here? Well, on the top we have to get from moles of NaOH to grams of NaOH. On the bottom we have to get from liters of solution to nothing. There's nothing on the bottom there. So you're going to have to make two conversions. The way I recommend doing these problems is do it one part at a time. Do the top first and then do the bottom. Or you could do the bottom first and then do the top. But do one part, either top or bottom, all at the same time. So to get from here to here, I'm going to give you 1 mole. Go to your periodic table and look it up, but 1 mole of NaOH. And sodium is 22.99. Oxygen is 16. Hydrogen is 1.01. That's going to equal exactly 40. there's the molar mass conversion for NaOH. 1 mole is 40 grams. Okay, so let's take care of this, getting moles to grams first of all. So we need grams to appear in the final answer. We need moles of NaOH to cancel out, so we're going to do it like this. And just to save a little space, I'm just going to drop the zeros for now. So moles cancels with moles, and I have grams of NaOH, which is what I want in my final answer. Okay, now we've got to get liters to totally disappear. Okay, what we have up here to work with is 500 milliliters. So you see that there's a connection between liters and milliliters. So first, let's convert liters into milliliters. Okay, liters of solution cancels with liters of solution. Now we have milliliters solution on the bottom. We need to get rid of it. So very simply, we put this up on the top. You choose, you can put a 1 underneath it, but you don't need to do that. But if it makes you feel better to have it as a fraction, you can put a 1 down there. So milliliters, that's of solution, milliliters of solution. So now we've gotten rid of everything on the bottom, so there's nothing on the bottom. The only thing we have left on the top is grams of NaOH. So you multiply everything on the top, 1.2 times 40 times 500 divided by 1,000. And that gives us 24. And we're limited to 2 sig figs, so we're going to leave it at 24. Okay, there's the answer to that. All right, let's keep going. Okay, you want to create 347 milliliters of 2.3 molar ammonia, NH3 solution. How many grams of NH3 would be required? So when you see the word grams, you know you're going to need a molar mass conversion. So let's just go ahead and do that. Nitrogen is 14.01. 3 H's is 3 times 1.01. That would be 3.03. Add that to 14.01 and you have 17.04. Okay, almost off screen there. Let's do that. Okay, so we want to, how many grams of NH3 is what the question's asking for. So way over here. Okay, and what we're starting with is this. I think by now you can see we want to start with that. 2.3 molar, so that's 2.3. Okay, there you go. That's molarity. Moles, not per liter of NH3. Okay. All right, so let's see where we are. We start with moles of NH3. We want to end up with on the top with grams of NH3. Then on the bottom, again, you can lightly write a 1 if you want. There's nothing. It's just nothing. So that means liters goes away. So let's start with the top. There's our molar mass. So there's the molar mass. That's the ratio we want. We need moles of NH3 to cancel, grams of NH3 to end up on the top. So we're done with the top. We've taken care of the top. Now the bottom says we got to get liters of solution to disappear. So again, we have a conversion from liters to milliliters. So liters of solution, liters of solution. Now we have milliliters of solution on the bottom. Up here we have 347 milliliters of solution. So be clear, it's not just 347 milliliters, it's of solution. So it has to be of the same thing, and it is. So we're going to put that up top. And again, if you want to put your 1 down on the bottom there, you can. So milliliters solution cancels there and there. The only thing left is the grams of NH3. There's nothing on the bottom. Everything on the bottom has been canceled. So now you go ahead and you multiply 2.3 times 17.04 times 1 times 347 divided by 1 divided by 1 divided by 1,000. And that gives us 13.6. Sig figs limit us here to 2, so If you were going to truly do sig figs, it would be 14. Okay? Okay, there you go. All right. So these are the problems we did in class. It's a second chance because you really want to have these fundamental calculations of these different measures of concentration down before you get into some deeper problems. All right? Okay, number 6. Now we're getting into molality. What is the molality, M, of 3.7 moles of LiOH in 0.89 kilograms of water? So let's define molality. It's small m rather. On top is moles of solute. That's the same as molarity. On the bottom is kilograms, not liters. So it's a mass, not a volume. It's kilograms of the solvent. In this case, that would be water. In almost every case in these problems, it'll be water. Okay, H2O on that. Okay? All right, so what is the molality? So it's asking for molality, so that's going to be, and you always break it into these component units. And the solute in this case is lithium hydroxide. That's the thing that's being dissolved. And the solvent, which we want kilograms of, is H2O. All right, and it says 3.7 moles of LiOH in 0.89 kilograms of water. So on top is, and on bottom, so there moles of LiOH is what I want to end up with. And here I have kilograms of water on the bottom, and that's what I want to end up with, is kilograms of water. So this is just a straight up simple division problem. That's a K. Kilograms of water. Okay, so I've got the units on the top and bottom that I want, so just go ahead and do 3.7 divided by 0.89. And you get 4.15. You have two significant figures there, so you can call it 4.2. Okay, that was easy. Okay, what is the mass percent? So let's understand what mass percent is. So mass percent is, and you can write it like this, mass percent is grams of solute plus grams of solvent in the denominator. There could be more than one solute, so you would have to add the grams of this solute that you're interested in plus grams of any other solutes that you have plus grams of solvent. So it's the total mass that's in that beaker that you're mixing it, okay? And that's it. And then you multiply by 100%. You multiply by 100 and then put a percent sign on the end. All right. So it's 8.0 grams of strontium oxide and 45.2 grams of solution. So the solution already means that these two are added together. It's the strontium oxide and the water added together, the grams of that. So you don't have to do that math. So it just simply becomes, this problem simply becomes this. And I get 0.176. We got two significant figures there. So I'm going to put that at 0.18. Now you have to multiply that by 100%. And that will equal 18%. So 18% of the mass in the beaker, if you took the total beaker and massed it, weighted on the scale, 18% of that mass would be the strontium oxide. Okay? There you go. That's your final answer. Okay. What is the mole fraction, and that's chi, that Greek letter chi, of 25.2 grams of KCl plus 102.4 grams of H2O? All right, so mole fraction, chi, is going to be moles of your solute. And I didn't write the official formula here. Let me do that, actually. Over moles Okay, there you go. So it's moles, in this case, it's moles of solute over moles of all solutes. If there was more than one solute, you would add them all together. So moles of KCl, moles of H2O. So let's go ahead and do that. Sign. And that's going to be... Okay, so first of all, what we have to do is you have to do a molar mass conversion. I didn't give it to you in moles. I gave it to you in grams. Okay? So let's sneak that in down here. So for KCl, potassium is 39.10. So just get out your calculator if you don't want to do that mentally. And you're going to add that to Cl, which is 35.45. And that gives us 74.55. So I can just write these down here. Okay, and for H2O, it's one you should almost have memorized by now. It's 1 oxygen and then 2 hydrogens. Okay, so that's the molar mass. And so I'm going to try to squeeze this in. I don't know if I'm going to fit it all here. We now have to figure out how many moles of each of these we have. So I'm going to come way over here. See if I can do that. And I'm just going to use a second piece of paper here. So there we go. You might need a second piece of paper for this one, or just do it off to the side. Okay, so it's going to be for potassium chloride, it's going to be, we have 25.2 grams. And we need to get grams on the bottom from our molar mass conversion, so it's going to be 1 mole on top. Okay, so grams of KCl, it's going to cancel out. And you're going to divide 25.2 by 74.55. And we get 0.34 moles of KCl. Okay, I'm going to cover this up for a second because I got to do the other one. And that's going to be 102.4 grams of H2O. Okay, so grams of H2O cancels and cancels, so it's 102.4 divided by 18.02. And that's 5.7. Two significant figures we'll do on that. 5.7 moles. So these are the two numbers we're going to stick in the equation. Okay, so I'm going to come back here, and on the top I have 0.34 moles of HCl, KCl, excuse me, over 0.34. And then you have to add that to the moles of water. That's the 5.7. Okay, so you're just going to add those up, and you do not multiply by 100 with a mole fraction, and it's misleading the name a little bit. It's not really a fraction. Okay, by the way, it should be 0.34. I don't know why I wrote that there. Okay, and what you get for that is 0.056. And if we're doing significant figures, we can do it to 3. And that's your answer. You don't multiply by 100. It's just, and it's not a fraction, it's a decimal. That's why the name's a little misleading. You just express it as a decimal number. Okay? So to review, you were given grams. You need to have moles. There's the general formula here for this problem. You need to have everything in moles, so you have to do a molar mass. And we did that. We converted the molar mass and then compute the molar mass of KCl and H2O. And then you have to make the conversion from grams to moles for each of those. And once you do that, now you can plug them into this equation. They're in moles. Everything's in moles, and that's the answer that you get. It has no units of measure. You'll notice moles of everything cancels out, so it does not have units of measure. Okay, let's go on, and we'll finish up this video with this particular problem. It's parts per million. Okay, so parts per million is grams of solute over grams of solution, not solvent. Always be careful whether that denominator is solvent or solution. Solution is the two of them mixed together. And so it looks just like mass percent, except instead of multiplying by 100%, you're going to multiply by 1,000,000. It's used for things in which there's very small concentrations, like we talked about that, like toxic substances in the drinking water. That's measured in parts per million or even parts per billion. So let's go ahead and do this one. So let's go ahead and write that down. It's called ppm, parts per million. Parts per billion would be ppb. And it's times 1,000,000. I'm just going to write 10 to the 6th to abbreviate it. That's 1,000,000 right there, okay? All right, so let's go ahead and plug in our numbers. Now, notice what you have here is you have a solute, grams of arsenic, and you have kilograms of water, which is a solvent. So there's two little complications here. You got to get from kilograms to grams, and then after that, you have to convert. You have to add the solute and the solvent together to get the solution, because that's really what you want. So let's, rather than try to do that one long equation, let me just draw a line here. I'm going to go ahead and do this conversion down here. So 2 kilograms is 1,000 grams. That's one you should just have memorized. Kilo means 1,000, okay? So your conversion is 1,000 grams for every 1 kilogram. Doesn't matter what you're talking about, so you don't have to put solute solution here. It's kilograms, that equals 2,000 grams. So we have 2,000 grams of water, okay? So now we're going to set up this problem. Okay, so the solution is the solute, that, plus the solvent, that. You have to add those together to get the grams of solution. And then you're going to multiply that all by 1,000,000. I'll write it out this time. 6 zeros behind the 1. Okay, that's parts per million, okay? So go ahead and do the math on that. And you should come out with 99.99. So let's just call that 100. Okay, we're limited to 1 sig fig there anyway, so 100 is 1 sig fig. And that is ppm. Okay, everything here was in grams, so they're all going to cancel out. So it's 100 parts per million. All right, so for every 1,000,000 molecules, 100 of them will be arsenic, and the rest, which if you do the math on that, is 999,900 will be water. Okay, and if you add those two numbers together, the 999,900 plus 100 will give you 1,000,000 total. Okay. All right. So we're going to wrap this video now. The rest of the problems are more challenging, and that's okay. You just dive into them, guys. You just jump into these problems and start working them. And we're going to work a lot of these. We're going to work a stoichiometry problem every day for the rest of this class. It'll be part of every assignment. Be sure you get practice at these. Don't be afraid of them. The more you do and the sooner that you do them, the quicker you become good at this. Just remember that. So don't back off of them. So we'll start with this one down here on the next video. Okay, we'll see you then.